Hello, I'm Pawan Singh from Kausalya classes. Our topic is circular motion. Today we are going to discuss circular motion and our topic is angular variables. Angular variables. To start our lecture, first we should draw a circle because our topic is circular motion. So it is the basic diagram which we should make to start our lecture. Let us suppose this is a circle with the center O and a radius r, and this r is along x-axis, and for a particular instant you can say a particle p is moving and the position of the particle is p somewhere here, which is making angle theta with the x-axis. After time delta t, when we are changing the time in a small change, as I told you, this particle P is moving in a anti-clockwise direction, and at a particular instant the position of the particle is somewhere here, which is making angle theta with the x-axis. After a small change in time, let us suppose in delta t, this P changes its location from P to this new P dash, and after the variation in time, the angle also varies and angle changes, or you can say angle has increased its value delta theta. So here you can say this theta is nothing but the angular position, because in Cartesian system you can describe any point with the help of x-axis and y-axis and z-axis, and in this format, in polar format, you can say you can describe the position of the particle with the help of radius and angle. So this theta is called angular position, which is going to change once the time will increase. So for a small change in time, the theta also changes. So you can say the rate of change of angular position is called angular velocity, which can be represented by this symbol omega. Okay, so angular velocity is nothing but the rate of change of angular position, and angular position is what? Angular position is theta. So mathematically we can represent this omega is equal to, when time tends to 0, the change in angular position with respect to change in time, that is nothing but the d theta by dt, which says a rate of change of angular position with respect to time gives the angular velocity. Now, the rate of change of angular velocity, the rate of change of angular velocity, that is omega, is called angular acceleration. Angular acceleration, which is represented with the different symbol that is called alpha. So alpha can be written as d omega upon dt, or you can say double differentiation of angular position this is angular acceleration. So if the angular acceleration is alpha and it is constant, if angular acceleration is alpha and if the alpha is constant, then we have first equation, theta, that is angular position, is equal to initial angular velocity into time plus half angular acceleration into time square. This is the first equation. Second, final angular velocity is equal to initial angular velocity plus angular acceleration into time. Third, final angular velocity square is equal to initial angular velocity square plus 2 angular acceleration into angular position. Here, the symbols represents the different physical quantity. Theta is angular position, angular position, omega naught initial angular velocity, final angular velocity, angular acceleration, angular acceleration. Now you can think in a different way, and that is uh, the linear distance. The linear distance in the previous example, let us suppose this is r and the position of the particle was somewhere here at p and it changes to new position p dash. So the linear distance of p to p dash means the linear distance pp dash traveled by the particle in time delta t is given by delta s is equal to r delta theta. That is, once we are going to differentiate this value, delta s upon delta theta is equal to r delta theta upon delta t, which is going to give ds upon dt is v is equal to r omega. So we have stabilized one relationship between the linear velocity as well as angular velocity, and here you can say linear velocity is equal to r times angular velocity, and this is deduced by the concept as we have studied in our previous classes that theta is equal to L upon arc upon radius. So arc is equal to theta into radius. So for a small change we have differentiated and we got the answer, and we made the relationship between these two physical quantities, where v, this v is called linear speed. Linear speed because we have taken the linear distance. So once this is the p to p dash as nothing but the linear distance, you can say a linear distance. Linear distance is p to p dash. So the distance is equal to r times delta theta, and we have differentiated. So this v is linear speed. It's not linear velocity, it's linear speed. So this v is linear speed of the particle, and differentiating this equation, let us suppose this is equation 1. Once we are going to differentiate, the differentiation of dv by dt is equal to r is a constant, so it will come out d omega by dt will give us at is equal to r alpha. See, The differentiation of angular velocity with respect to time will give the angular acceleration. This is confirmed. So right hand side you don't have any problem. But look at the left hand side. Is it acceleration? No, because this v is not velocity. This v is linear speed, not the velocity. So the differentiation of linear speed will give the acceleration component, not the acceleration. Let us suppose someone is moving in this direction with the 5 km per hour. Let us suppose this is a y-axis, okay, and this is the x-axis. So if someone is moving in this particular direction with the speed of 5 km per hour and making angle 37 degree from the x-axis, you can say that this particular person is moving in x-axis with the 4 km per hour and y-axis at the 3 km per hour. Then only this 5 km per hour will justify for this particular case. So this 4 km per hour is just the component of 5 km per hour in x-axis, and this 3 km per hour is just the component of 5 km per hour in y-axis. You should have this concept in your mind, then only you will understand whatever you get here is not the acceleration, it may be the component of the acceleration, because you have taken linear speed, not the velocity. The differentiation of velocity with respect to time will give the acceleration, but linear speed differentiation will give the acceleration, but that will not be the actual acceleration, maybe the part or the component of the acceleration. So at, basically in this particular case, at is equal to dv by dt is the rate of change of speed, and is not the rate of the change of velocity. Got it? So it is therefore not equal to, so it is therefore not equal to the net acceleration. So at is equal to dv by dt is the rate of change of speed and is not the rate of change of velocity. It is therefore not equal to the net acceleration. Okay, so you can say that at is the component of acceleration along tangent. This is at is the component of acceleration along tangent. So the new name of this at is tangential acceleration. Tangential acceleration. It means, let us suppose someone is moving in a circular path, so the acceleration we don't know about the net acceleration, but whatever we are getting in this direction is just the differentiation of the linear speed. So this will give the at, and that is the tangential acceleration, means the tangent at the point where the particle reached. So this is what the concept I wanted to discuss with you. In the next topic will discuss the unit vector along the radius and the tangent. Thank you.